Hello Year 12 chemists, welcome to TP's Chemistry Cuts. In this video we start by describing the particle model of an ionic substance. We then move on to use this model to explain a number of physical properties of ionic substances.
Okay, in a very generalised sense, then ionic compounds or ionic substances are formed when you take a metal and react it with a non-metal. And what we have to do to sort of justify this is go back and look at the nature of metals versus non-metals in terms of electrons. Okay, if we look at the metals, where are they in the periodic table? How do we know where they are in the periodic table? What tells us? Sorry? Yes, well that's all that, but in terms of just looking at the periodic table, how do we know where they are? Where are they? To the left. So if we look at that periodic table there, in a very faint red line step, we've got this, okay, this step in faint red. Everything to the left is a metal, everything to the right is a non-metal. That's what you learnt earlier on. That should be still fixed in your brain. Okay, so metals in general, waving the arms a bit, not always true, but in general have less than half-filled valence levels. Okay, so if they've got less than half-filled valence levels, it's easier for them to empty them out so that they have only filled levels and gain stability rather than actually fill them up. They've got to put more electrons in to fill them up than they have to lose. So they lose. Okay, so they lose electrons to empty their valence level, and when they do that, they gain stability because they're made, or their electron configuration, electron arrangement is comprised solely of filled levels, so that gives them an extra bit of stability. And okay, so the important thing then is once they've lost those electrons, they form cations. We're expected to use that word now rather than positively charged ions. Okay, so they have a positive overall charge, and the reason is because they've got more electrons now than, more protons than electrons. So if we look at non-metals, it's the reverse situation. So that's basically, in a couple of minutes, what you've done in the last 2 years. Okay. And what this means overall, okay, that we're transferring electrons from the metal to the non-metal. So that's what we are in effect doing when the reaction occurs. Now, what we're really interested in is what happens next. That is not the end of the story, because you form these ions. These ions aren't just sort of randomly spaced out in relative to each other. They can't be, because what you have are oppositely charged particles, and the way things work is that opposite electrical charges always attract. So these ions now then attract each other. If you look at an individual ion, so for example, if we had, don't draw this for the moment, but say we had this, that positive charge is distributed evenly over the surface of that ion. It's not on one side, it's not localized at all, it's delocalized around the whole atom. And that means then that when that positive charged ion comes anywhere near a negative charged ion, regardless of which direction it is, it will attract, that one will attract ions of opposite charge from all directions. And it's the same with the negatively charged anions. They will also attract positively charged cations from all directions. Okay? And the overall outcome of that is that these ions always form into large three-dimensional arrays that we call lattices. and you get this alternating plus minus effect. Okay? So let's put that all up. It's all pretty straightforward stuff. But the nature of that attraction is what we call an electrostatic attraction. The word itself says what it is. It's electrically based, that's what the electro bit. Static means it's formed and stays on each of the ions. And so those oppositely charged ions attract each other, and that's called an electrostatic attraction. Okay? So that's a two-dimensional representation of it. But the point is that each negative charge, so this one here, is surrounded in contact with positive charges. And there'll be a positive charge on top and a positive charge below. So this is a three-dimensional effect. It's not sheets. No individual sheets. It's a three-dimensional lattice. So that's basically what they look like. What we need to know a bit more is the nature of that electrostatic attraction. Is it strong? Is it weak? How do we know? It's a very simple answer to that. If we look at one of those properties, and that's melting point, boiling point. So we're going to look into that in a little bit more detail. What are we actually doing when we melt something? I know we're changing it from a solid to a liquid, but what actually happens at the particle level? The solid, what's happening is the particles are actually locked in place relative to each other, yes? They can't move relative to each other. They can vibrate, but they can't move over or past each other. So, in terms of their position relative to one another, the surrounding ones, they're in fixed positions, but they vibrate, okay? When you melt something, what you're doing is you're allowing them to suddenly move over each other, because in a liquid, particles can move past each other. They're not fixed relative to each other, they can move past each other. And so to be able to do that, you've got to do something. Why is it that in a solid, the particles can't move? What stops them? Yes, that's exactly right. The forces of attraction between the particles in the solid are so strong, they lock them in place. So all they can do is just vibrate about a set position. So what's happened then is, if you suddenly allow them to move, you must have broken down those forces to some extent. Yeah? So you need to do something like put energy in to do that. And that's why we call it a melting point. It's the point at which you put sufficient energy to actually melt, break down those forces sufficiently to allow particles to move over each other. And it's just a little leap of faith, if you like, that if you've got a higher melting point, what does that tell you about the forces acting between particles compared to something that's got a lower melting point? They're stronger. You need more energy, so they're stronger. You're having to break something that's much harder to overcome by putting more energy in. And so, as a general rule, the higher the melting point or boiling point of the substance, because boiling point is just taking it to the next stage where you completely break down forces so the particles can move from one another, completely away from each other. Okay? So melting point and boiling point are both good measures of how strong the attractions are between particles. And that's why ever you come across something where you need to discuss boiling point or melting point, what you're talking about is strength of attraction between particles. It's always about the strength of attraction between particles. Some of the other physical properties that we'll deal with, we're not looking at that. But melting point and boiling point is about the strength of attraction between particles. Could I rub that out there? Because I think that's so important. We need to write a few notes about it and go through them again. Because you're going to need to write explanations when you compare one thing with another. When you're comparing one type of force with another type of force, one type of bonding with another type of bonding. If you have a very big difference in your melting point, you're going to have to say something about what that tells you about the nature of those forces, how strong they are. So you need to be able to explain it, and so we'll do that now. part of that sentence there is you've supplied sufficient force, energy to break down forces. Okay, you're supplying energy, and what that energy is doing is breaking down forces between particles. So as it follows then, that the higher the boiling point, melting point, the more energy you've got to supply to break down those forces. And if you've got to supply more energy to break down the forces, those forces must be stronger. Okay, so the higher the melting point, the stronger the forces between particles. And that's what we're aiming for. And that's the really important thing. That's what we're aiming for, is that bit there at the end. And the sequence of logic that's there. What often people will say is the higher the melting point, the stronger the forces. The problem is you've not linked the two things together. You must link them. So, you say the higher the melting point, the greater the amount of energy supplied to break down forces. Then it makes sense to say the stronger the forces. Otherwise, you've left a bit out. You've got to explain your reasoning. And so that central bit, the greater the amount of energy that must be supplied to break down the forces, is absolutely critical. If you leave that out, you're going to lose excellence. Okay? So that's the link. With boiling points, it's a very similar argument. But rather than saying you're going to partially break them down, you're actually going to fully break down all the forces between particles so that they can move away from each other completely. Okay? Now, if you don't mind me repeating myself, what I can do is actually summarise that again in the middle. Do you want me to do that? Or not? You're going to be using all the time the argument you're going to be using. Okay? So obviously one of the things we're going to do as we go from particle to particle type, from substance to substance, we're going to home in first on the melting and boiling points. Okay? Do they have high melting points in general, low melting points, or something in between? Because that will tell us something about the strength of attraction. What's the remember, the nature of the forces acting between particles depends upon the type of particles. We can now see, for particular types of forces, whether they're strong or weak, depending on what their melting or boiling points are. Okay, so that's a very powerful tool in our arsenal. So why don't we start with ionic compounds? I think it says it all. If you look at all ionic compounds that you'll come across, they are all of them solids. All of them, no exceptions. Well, what does that tell you? What did we say about something that's a solid? The forces are strong in the solid. Okay? Sounds like Star Wars, doesn't it? Okay, so they're so strong that they do not allow particles to move relative to each other. And that's for all ionic compounds. So what that's telling you is that electrostatic forces in ionic compounds are actually very strong. And that's true. Generally, as a rule of thumb, they are strong. And so what you'll find is that one of the things that now characterises ionic compounds is they have high melting points and boiling points, all of them. So that's the first thing. So that's the thing, if we say, oh, this might be an ionic compound, let's have a look at its melting point. Oh, it's high, that's okay. Then we look at another property, then another property. Okay? But the first port of call is the melting point. Okay? Okay, so that's the important point. They've got high melting and boiling points, and that's because those electrostatic forces are very strong. And that's the sort of thing you've got to be able to justify with that intermediate sentence there. What I want to do now is to move on to look at some of the other properties that are consistent with that model now. So we've got these ions held together rigidly in place by very strong electrostatic attractions. How can we use that to explain other things? Okay. So the next thing is we're going to look at electrical conductivity. So now, for something to conduct electricity, it has to meet a requirement. What is that requirement? Electrons. What about those electrons? What are they doing? They're moving. Okay? And so if we look at electrical circuits, what we have is negative electrons. They're carrying the charge and they're moving around the circuit. Well, we're not dealing with moving electrons. The electrons have already moved. They've moved from the metal to the non-metal. So that's not the thing that's going to potentially cause electrical conductance. In fact, there's a more general description of what's necessary for conduction of electricity, and that is that you've got to have freely moving charged particles. Okay? And that actually includes electrons. That actually brings in that as part of the definition or description, if you like. But it also potentially opens it up to other things, because we do have charged particles in ionic compounds. We have ions. So let's start off by stating what the requirement for electrical conductance is. And if you get any question on this, anything to do with electrical conductivity, your answer must state that at some point. Okay, so let's have a look at ionic compounds. Do they conduct? And like many things, it's not as simple as that. They either do or they don't. It depends. So we need to look at 2 or 3 different scenarios. So let's look at, firstly, in the solid state. Now, ionic compounds do have charged particles. We have ions, that's the particle we're dealing with. Okay? The question is, are they freely moving in the solid state? And the answer is no, of course not. Because in solids, particles, in this case ions, are locked in position relative to each other. Why are they locked in position again? What about those bonds? Strong bonds. Yes, we've got strong electrostatic attractions between ions which are locking them in place. So they can't move. So do solid ionic compounds conduct electricity? No, they don't. Okay, no, they don't. So that's our starting point. Okay, so that summarises it nicely. You've got ions that are locked in position relative to each other by strong electrostatic forces. They can't move, so it doesn't conduct electricity. If, however, we melt an ionic compound, okay, what can we say about particles in a liquid? What happens to particles in a liquid? They're sliding over each other, aren't they? Sliding past each other. So they are freely moving. So when you melt a solid, you've got particles that can move freely past each other. And so if we melt an ionic solid, ions are suddenly moving past each other. They're freely moving, so they conduct electricity. Okay, so this is actually a very important point. This forms the basis of electrolysis in industry, where we, for example, recover aluminium from aluminium oxide. We do it by melting the aluminium oxide and then passing electricity through it. And because it conducts now, it enables us to extract aluminium. Okay, so this is a very important thing. There is another way of making ionic compounds conduct. Okay, perhaps a little bit more obscure, and that's by dissolving them. So if the ionic substance is soluble in water, so for example sodium chloride, you can dissolve it up in water, and what it does is it separates the ions. So those ions are now freely moving in a water solution, in an aqueous solution. So they are now freely moving, so the solution of the salt is now conducting. So anything that is soluble in water that's ionic will form a conducting solution. Okay, so what we have now is we're beginning to build a set of properties that are helping us to actually identify an ionic substance. So we've got something now that we know has been made up of a metal and non-metal, but if we didn't know that, we were given the substance and we had to discern what the particles were based on its properties. We know now that if it's going to be an ionic compound, it's going to have a high melting point. It's also not going to conduct when it's a solid, but it does when it's a liquid. So that's an unusual thing. And you can also form, if it dissolves in water, it will also form a conducting solution. Okay, so we're beginning to actually build up a suite of properties, if you like, that will actually help us to identify the nature of this type of solid. This last bit about the ionic salt dissolving in water is something we're going to go on to in just a second. So the next property we're going to look at for ionic compounds is hardness, and in a way it's their malleability and ductility. Okay, so if you look at hardness. Now these all form solids, and they're pretty hard solids. If you hit them with something, they do not flatten out at all into sheets. You cannot draw out an ionic substance into a wire. If you try doing that, or flattening into a sheet, and you strike it, it'll just shatter. I nearly said something I shouldn't have said then, didn't I? Okay. It'll just shatter. Okay, so that's the first thing. That's the important thing. They do not flatten out, they do not stretch into wires. So this is obviously a distinguishing point from metals. Now, there's a very simple explanation for this. So let's go back to our structure. Okay. So when you strike something, what you're doing is just applying a force to it. Okay? And what that will do with an ionic substance, okay, is it's going to cause particles to move relative to each other in a way that is easiest, along a line of weakness. And that is basically, if you look at this, they look like layers, don't they, on top of each other. You can sort of see layers if you were to build this up to be larger across the board. You've got a layer of plus minus, then another, then another. And when you apply force, what happens is layers of ions start to slide across each other. What's going to happen if this layer starts moving across relative to that layer? So this one moves across that way, this one moves that way. What's going to happen? Think about this ion. What's it going to do if it moves this way? That's not going to be good.
The negatives are going to repel and then push away from each other.
Yes. So if you slide these sheets over each other, this negative is going to come over this negative, this positive is suddenly going to be over that positive. Is that a good thing? The answer is no, because light charges repel each other. So that's why they shatter. You're moving them relative to each other, and suddenly they're in front of something that they really don't want to be in front of, and repel away. And that's what causes the shattering effect. Okay? Okay, so that's what's causing it. You've got layers of ions sliding over each other, causing cations to come into contact with cations, anions to come into contact with anions, and so they repel each other and that shatters them. The last part of this is solubility. This is just a general thing. The problem with ionic substances is that some are soluble and large numbers of them aren't. So we've got to try and work out why in terms of the model we've got. Okay? And the best thing to do, or the best way to go about that, is to first of all get clear in our minds what actually happens when something does dissolve. And that's what we've already talked about. What in fact is happening is you're taking particles, ions in this case, that are locked together by strong forces, and systematically you're separating them from one another by breaking those electrostatic forces, and they're moving into gaps between solvent molecules, and they're moving freely around, and that's how it dissolves. The question then, having taken that on board, is to think, why is that happening for some but not for others? What really is the overall picture going on here that actually makes it so that some will dissolve and some won't? And the answer is, it's all about what happens in terms of forces before dissolution and what happens after. So what I mean by that is, what we've got to do first is we've got to break some attractions. We've got to break all of these ionic attractions. And that takes energy. So if that was all we had to do, then nothing would dissolve unless we provide energy for it to dissolve. And yet if we look at salt, for example, sodium chloride, we can chuck it in water, swirl it round a bit, and that's not going to provide enough energy, but it suddenly disappears because it's dissolved. So something else happens once the particles are dissolved in the water. Now, you're going to have to take what I'm about to say on faith for the moment, because we're going to have to look at the nature of water molecules to explain what actually happens. And this is something that you're going to learn about a bit further on down the track. So this is what we're aiming for, and if it seems a bit confusing, just accept it for what I'm showing you, but we'll explain it later. Okay? So, there's a two-step process involved. We're breaking bonds, which means we've got to put energy in. Somewhere along the line, we've got to form some new bonds to get some energy back out. So that can be used to dissolve more things and so on. Okay? And the actual bonds that form are actually quite weak ones. Because if we actually look at water molecules, water is what we call a polar molecule. Okay? Now, a polar molecule is one where there isn't a nice even distribution of electrons, okay, in a molecule where they're sharing electrons. It's been distorted for some reason. Now, I'm not going to go into the reason why, but in water, the electron distribution is highly distorted, okay, because we've got oxygen, which pulls electrons towards it very strongly, and hydrogen, which doesn't. So, electron density, if you like, is pulled towards oxygen. So if we look at water, we can represent it like that. Okay, H2O, we all know it's H2O. And the distortion of charge that makes it polar, we can represent by putting a Greek delta. That means there's a build-up of negative charge on oxygen and a slight deficit of positive charge on hydrogen. Okay? Just accept that for the moment. Also, just accept that it's a V-shaped molecule. Okay? They're little deltas, Greek deltas. And it means it's a slight positive charge, not a full positive charge, just a little bit positive at one end. So it means there's a bit positive here and a bit negative there. So you can imagine it like it's a bit jelly-like, and somebody's pushed the jelly slightly to one side. Does that make sense? So where there's a build-up of the jelly on one side, that's your slight negative, and where there's a little depletion of the jelly on the other side, it's where it's slightly positive. But it's still all there being shared, so it's still not an ion. Okay? And that's what we call a polar molecule. We'll explain that later. However, when an ionic substance dissolves, what actually happens is you get weak attractions between these things and the ions. So if we've got delta pluses there, and there's a negative ion floating around here, these bits stick to it. And there'll be another water molecule, and another water molecule, because you've got huge numbers of water molecules compared to what you've got salt. Okay? And if you've got a chloride, it would be the same, but in reverse, with the hydrogen ends of water sticking on to the Cl-. So the delta pluses from the water attaching or being attracted to the Cl-. Now it must be emphasised these attractions are quite weak. But you can imagine, if it's been totally surrounded by water molecules, and both ions are like this, then they can add up to be quite substantial. And here's the rub. It's a comparison. What we're doing is first of all, we have to break down the electrostatic forces. That takes energy. What we're then doing, so we'll say this. We then form new attractions. Because energy is given out. Okay? So you've got energy going in and then energy going out. Now, if the amount of energy coming out is greater than the amount of energy going in, the salt will dissolve. If, however, the amount of energy needed to break down those forces is so large that you're not getting as much back from making these new attractive forces, then it doesn't dissolve. Now the easy way to say this is that if you take something like sodium chloride, what actually happens is that the ions separate and new attractions form between the separated ions and the surrounding solvent, water molecules, and those attractions are strong enough to literally pull ions out of the lattice. That's the best way to say it. Okay? If it's insoluble, then what it is that those attractions that form between separated ions and the surrounding solvent molecules are not strong enough to pull ions out of the lattice. Okay, so it's all about the relative strengths of these types of forces, where there's an awful lot of them, and these which are stronger, but there are fewer of them. Okay, and it's a case of the balance, and I think that nicely summarises it. Now there is a potential that you might be asked that, so that's why I've gone through it. That basically finishes off ionic compounds. In the next lesson we're going to move on to metals.